New images reveal that the third interstellar atlas has no tail. The finding has shaken the astronomical community because it contradicts everything known about comets and interstellar objects crossing our solar system. For weeks, telescopes across the globe followed this mysterious visitor that seemed to behave like a common comet, but now appears as a simple sphere of diffuse light, without any trace of gas or dust. How is it possible that such a bright, so active body does not leave behind a visible trail? While data continues to arrive, the questions grow. The third interstellar atlas approached the Sun, increased its brightness, changed color to an intense blue tone, and yet the most sensitive cameras did not detect the typical tail that should have formed from the sublimation of ices. For some scientists, this represents a physical enigma. For others, a unique opportunity to study how materials behave in an object coming from another stellar system. Before we dive into the mystery of the third interstellar atlas, you need to do 3 things immediately to activate the scientific community. First, give a like to this video to push this discovery to more observers. Second, subscribe and activate the bell to receive the next updates about the tracking in real time. And third, go down to the comments right now and write Cosmos to join the global registry of those who are following this historic event. Do it now. Today we are going to analyze what the latest observations reveal. What does Professor Avi Loeb think? And why has this object become one of the greatest astronomical mysteries of the year? The third interstellar atlas was discovered by the Atlas Observation System in Hawaii and confirmed as the third known interstellar object traversing our solar system. Its hyperbolic trajectory demonstrates it is not gravitationally bound to the Sun, which means it comes from interstellar space. Since its detection, it has been monitored by telescopes in Chile, Spain, the United States, and also by instruments from NASA and the ESA. After its passage behind the Sun, it reappeared with unexpected behavior. Its brightness increased 5-fold and its color became bluer. This change drew attention because it is usually related to cometary activity, that is, with the release of gases and particles. However, the most recent images obtained with high-resolution telescopes showed that the third interstellar atlas does not have a visible tail, nor a dust cloud, nor a gas trail, nothing, only a diffuse light that seems to float in the void. That absence has opened an intense debate among astronomers. Could it be a comet that lost all its volatile mass? Or is it perhaps a rocky fragment different from any other we have seen? In the most recent interview, Professor Avi Loeb from Harvard University expressed his surprise. With the level of solar radiation received, approximately 770 watts per square meter, a dense cloud of gas and dust should have formed, but the images prove the opposite. The announcement arrived quietly, but its impact was immediate. The observatories tracking the trajectory of the third interstellar atlas object published new images processed during the first weeks following its passage through the perihelion, the point closest to the Sun. What was observed perplexed everyone. The luminous structure showed no signs of a tail, no dust line, no gaseous trace extending behind its nucleus. Only a diffuse, compact mass, as if the solar radiation had failed to tear away even a single grain of material from its surface. For an active comet, that is almost impossible, but for an interstellar object, it could reveal something more profound about its composition and origin. Initially, the third interstellar atlas was detected by the Atlas Alert System in Hawaii, in early 2025. Its hyperbolic trajectory indicated from the beginning that it came from outside the solar system, thus becoming the third known interstellar visitor after Oumuamua in 2017 and the second interstellar Borisov in 2019. However, from its first observations, it already showed unusual behavior. While the second interstellar Borisov presented typical cometary activity, a bright tail composed of gases and dust, the third interstellar atlas seemed more stable, more compact, as if its surface resisted the solar heat in a distinct way. Some astronomers interpreted this as a sign that the object could have a denser composition with a nucleus rich in metals or with ices trapped under a layer of refractory material that protects them from sublimation. The images obtained after its reappearance, once it passed behind the Sun, reinforced the mystery. The intensity of its light increased considerably, approximately 5 times brighter than during its previous approach, and its color changed towards a pale blue tone. In physical terms, that type of change can be due to the exposure of new materials on the surface or to the scattering of sunlight in extremely fine particles. But the surprising thing is that despite that transformation, the telescopes did not capture signs of cometary activity. There was no clear spectral evidence of gas molecules like carbon monoxide or cyanide, nor diffuse halos indicating the presence of dust. In other words, the third interstellar atlas behaved like a solid object reflecting sunlight, not like a comet releasing matter. Professor Avi Loeb from the Harvard-Smithsonian Center for Astrophysics was one of the first to react publicly to the absence of a tail. In interviews and academic publications, he explained that with the level of solar radiation the object received, estimated at approximately 770 watts per square meter at its closest point, any body composed of volatile ices should have released a considerable amount of gas. That release would produce a non-gravitational acceleration, a small thrust that slightly modifies the object's trajectory. Indeed, some initial calculations suggested that this acceleration existed, although at very low levels. But if there really was a non-gravitational force, where is the material that generated it? That is the paradox that has kept scientists debating for months. The data collected by the NIRLAB telescopes and the Las Cumbres Observatory indicate that the nucleus of the third interstellar atlas has a diameter of approximately 5 kilometers with a mass exceeding 30 billion tons. With that density, any mass loss should be detectable, at least as a faint cloud around the nucleus. However, what the cameras recorded was a concentrated light source, with defined edges and no visible dispersion. Some researchers suggest that the object's orientation could explain part of the phenomenon. If the rotation axis were aligned with our line of sight, the possible tail could be hidden behind the nucleus, becoming almost invisible from Earth. But even under that hypothesis, changes in the polarization of light should have been detected, and that did not occur either. Other astronomers proposed that the volatile materials of the third interstellar atlas could be different from those of conventional comets. Instead of water, carbon dioxide, or ammonia, it might contain heavier compounds that sublimate at much higher temperatures, which would make the activity minimal at the distance it passed. That idea coincides with the absence of known spectral signals. The possibility has also been considered that its surface is covered by a crust of metallic minerals that prevents the release of gas. In that case, the solar heat would only affect a superficial layer, producing color changes without generating a visible tail. None of these explanations has been confirmed, but all reflect an attempt to understand a phenomenon that challenges current models. What is proven is that the object represents no danger to Earth. Its trajectory, calculated with precision, will take it to a minimum distance of some 280 million kilometers from our planet in December 2025. From that position, space telescopes like the James Webb and the Hubble plan to conduct new observations to analyze the composition of its light. If spectral lines associated with gases are detected, that would confirm that some activity exists, even if extremely weak. But if the spectrum remains flat and lacking those chemical fingerprints, then the third interstellar atlas could be classified as the first interstellar object with no apparent cometary activity, a body that preserves its integrity despite the heat of the sun. The scientific interest in this visitor is not only for its rarity, but because it offers an opportunity to study how objects beyond our system form and evolve. Each of these interstellar travelers carries with it information about the physical and chemical conditions of other stars and their planets. If the third interstellar atlas does not release gases, that could mean it comes from a colder region or that it was exposed to stellar radiation for millions of years, enough to harden its surface. In either case, its behavior expands the boundaries of what is known about the bodies that wander among the stars. Avi summarized it with a phrase that has gone viral among the scientific community. Sometimes the universe reminds us that we do not have all the answers, and the third atlas seems to be one of those reminders, an object that does not conform to the rules, that surprises even the experts, and that for now remains an enigma that challenges human understanding. The nights following the announcement were filled with activity in the most important observatories in the world. Teams in Chile, Hawaii, Arizona, and the Canary Islands began reviewing their data to confirm if the absence of a tail in the third interstellar atlas was real or a product of an instrumental limitation. In astrophysics, details matter. The orientation, the detector's sensitivity, or the contrast with the background light can completely change an interpretation. Even so, after several cross-analyses, the result was consistent. There was no visible tail nor a detectable dust cloud in the photometric records. The images of the third interstellar atlas continued to show only a compact source, something that more closely resembles an illuminated asteroid than an active comet. In strict terms, a tail is produced when solar radiation exerts pressure on the gas and dust released by a comet's nucleus. That thrust creates a stream of particles that extends in the direction opposite the sun. If the object does not release material, there is nothing that can form that luminous trail. However, the measurements of its brightness and the slight deviation of its orbit suggested some type of activity, however minimal it might be. This led scientists to a more complex hypothesis. Perhaps the third interstellar atlas is releasing material, but in such a small quantity or with such a large grain size that the particles do not reflect visible light. In that scenario, the tail would exist, but it would be invisible to the human eye and could only be detected at infrared or radio wavelengths. To test that idea, observations were scheduled with radio telescopes in Europe and North America. So far, the preliminary data do not show a significant emission of volatile molecules. The characteristic bands of water, carbon monoxide, and cyanide, which are usually the easiest to identify, are absent. The spectrum of the third interstellar atlas is surprisingly flat, which implies the object reflects sunlight without absorbing it selectively. That is a typical property of rocky surfaces covered by dark minerals or by metals that have undergone processes of space oxidation. That is to say, it behaves more like a hardened interstellar rock than like a disintegrating icy body. In an article published in October, the team from the Gemini Observatory proposed that the bluish coloration of the third interstellar atlas could be due to the presence of recently exposed silicates. When a body of this type approaches the Sun, the heat can fracture the surface layer, revealing fresh minerals that reflect blue light more intensely. That explanation fits with the observed color change, but not with the lack of activity. If there was surface fracturing, there should have been small ejections of dust. The contradiction persists. Everything indicates that the object experienced an intense heating process, but without releasing matter into space. Professor Avi Loeb, in a recent conference, compared the phenomenon to that of a polished metal rock that shines when heated. According to him, the third interstellar atlas could have a much higher density than that of known comets, which would make its internal gravity hold the surface together and prevent the expulsion of gas. Loeb emphasizes that for now there is no evidence of anything artificial, but there is evidence of physical behavior that requires new explanations. His words were taken out of context in several media outlets that insinuated the possibility of a technological origin. In reality, his message was more prudent. The object does not fit with current categories, and that makes it a natural laboratory for science. In parallel, NASA's Center for Near-Earth Object Studies published a report that supports part of that view. Their calculations indicate that the non-gravitational acceleration of the third interstellar atlas is so small that it is barely distinguishable from measurement errors. In other words, if that additional thrust exists, it is extremely weak. According to that data, the object's trajectory can be completely explained by the action of solar gravity. This contradicts the initial hypothesis of a significant acceleration, but it also leaves open the possibility that there are subtle processes that have not yet been measured with precision. Astronomers have taken advantage of this opportunity to compare the third interstellar atlas with its interstellar predecessors. The first, Oumuamua, also presented strange behavior. It changed its speed without showing signs of gas or dust, which generated a debate that still continues. In the case of the second interstellar Borisov, on the other hand, everything was simpler. It behaved like a typical comet with a clear tail and constant activity. The third interstellar atlas seems to be located at an intermediate point, a hybrid between the two with characteristics that recall both, but without totally coinciding with either. This comparison is fundamental because it could mean that different types of interstellar objects exist, formed under different conditions in their systems of origin. Numerical simulations indicate that its trajectory will take it out of the solar system by mid-2026 and that it will never return. Every observation counts because this is the only opportunity humanity will have to study its behavior up close. The coming months will be decisive. In December 2025, the object will reach its closest point to Earth, some 280 million kilometers. A safe distance but sufficient for space telescopes to capture finer data. The James Webb Space Telescope team plans to analyze its spectrum in the infrared to search for signals of molecules that are not detected in the visible range. If Webb finds traces of ammonia ice or trapped methane, it will be confirmed that it still retains volatile materials, although in minute quantities. If it detects nothing, then the hypothesis of a totally inert surface will gain strength. The scientific discussion is intense but respectful. In conferences and virtual forums, researchers share graphs, light curves, and simulation models. Some think we are facing a new type of interstellar body, a kind of exotic asteroid hardened by cosmic radiation for millions of years. Others believe that we are simply observing a comet in a final stage of its evolution that lost the capacity to release gases. Both positions are possible, and only the upcoming data will tip the balance towards a definitive conclusion. Meanwhile, the public follows the topic with fascination. Videos of the conferences and publications from the observatories reach millions of views. The image of an object coming from another stellar system, silently crossing among the planets and defying human expectations, awakens something more than scientific curiosity. It provokes awe, humility, and a feeling of smallness before the immensity of the cosmos. In a certain way, that collective reaction is also part of the value of the discovery. The Third Interstellar Atlas not only tests our instruments, but also our capacity to accept that the universe always has something new to show us. Avi Loeb summarized it in a simple phrase during a recent interview. It is not that the object is mysterious. What is mysterious is our lack of knowledge about how matter behaves outside our stellar system. And that idea captures the spirit of all this research. Each piece of data, each image, and each analysis brings us a little closer to understanding not only what the Third Interstellar Atlas is, but also how diverse the worlds that exist beyond the Sun can be. As the weeks following the perihelion advanced, the attention of the astronomical community concentrated on the smallest details of its behavior. The Third Interstellar Atlas, which had already surprised with its lack of a visible tail, continued to offer challenges to theoretical models. The light curves obtained by the follow-up telescopes showed a pattern of slight but periodic variations, as if the object rotated slowly on its axis. The most precise analyses indicated a rotation close to 14 hours, a relatively slow rhythm if compared to common comets that usually rotate in a few hours. This data reinforced the idea of a solid and compact body, with a structure capable of maintaining its integrity without fragmenting, despite the thermal and gravitational forces to which it had been subjected. The team from the University of Maryland, specialized in the dynamics of small bodies, analyzed the brightness changes and concluded that the surface of the Third Interstellar Atlas could be composed of materials with different levels of reflectivity. That would explain the small fluctuations in its luminosity, but the most important thing was that the researchers found no evidence of gas release or particles that could justify the non-gravitational acceleration detected at the beginning. With each observation, the hypothesis that the Third Interstellar Atlas was an active comet lost strength. On the other hand, the astronomers from the European Southern Observatory used high-resolution spectroscopy to try to detect chemical signatures. If there were water ice or carbon dioxide sublimating, specific absorption or emission lines should appear in the spectrum, but the results were negative. What was observed was a continuous, flat spectrum without characteristic peaks. This type of spectrum is typical of solid materials covered with dark dust, like basalt or oxidized iron. While that does not completely rule out the presence of ice in the interior, it suggests that the surface layer is sealed, preventing the exit of gases. At the same time, the updated orbital calculations by NASA confirmed that the Third Interstellar Atlas follows a hyperbolic trajectory that will take it back to interstellar space in 2026. After December 2025, its brightness will diminish rapidly and it will be impossible to observe from Earth. This narrow margin of time has prompted a race against the clock among the most powerful observatories in the world. Every clear night counts, every piece of data can be crucial to understanding the nature of this visitor. The behavior of the Third Interstellar Atlas has inevitably awakened comparisons with that of Oumuamua, the first detected interstellar object. In that case, the absence of a tail and a slight non-gravitational acceleration led to multiple interpretations, some even beyond conventional physics. But unlike Oumuamua, the Third Interstellar Atlas does show a weak coma and slight spectral activity at specific wavelengths. That suggests that although the activity is small, there exists some level of interaction with solar radiation. The difference is that this activity does not produce a perceptible tail, which could be due to a combination of factors: particles too large to reflect visible light, gases that dissipate rapidly, or an emission geometry pointing away from our field of view. One of the most debated hypotheses proposes that the Third Interstellar Atlas is coated with a layer of refractory material, a kind of cosmic crust formed by metallic minerals that prevents the internal ices from escaping. This type of surface could form over millions of years in interstellar space, when radiation from nearby stars hardens the material and provokes chemical reactions that seal the pores of the nucleus. If this theory is correct, then the Third Interstellar Atlas would be a natural capsule, an intact fragment from another stellar system preserved in the vacuum. That would make it an object of the highest scientific value because it would contain information about the physical and chemical conditions of its place of origin. The interest of astrophysicists also focuses on the internal structure of the object. Thermal models suggest that despite the intense heat received during the perihelion, the temperature in its nucleus did not exceed 150 Kelvin, which is equivalent to approximately 120 degrees below 0 Celsius. At that temperature, the most common ices, like water or carbon dioxide, could remain solid if they are covered by an insulating layer. This would explain why large gas emissions are not observed. Instead, localized microleaks could occur, sufficiently small to generate minimal acceleration without creating a visible tail. It is a possibility coherent with the acceleration limits published in the recent studies. The other great unknown is its blue color. The analysis of the Hubble images indicates that the chromatic change became more evident after its passage behind the Sun. Under normal conditions, heat tends to darken comets, not make them bluer. This unusual behavior has led scientists to consider more complex optical processes. One possibility is Rayleigh scattering, in which very fine particles scatter blue light more efficiently than red light. If the surface of the third interstellar atlas fragmented into extremely small grains, the reflected light could acquire that bluish tone. Another option is that the exposed minerals contain iron or silicon in oxidation states that modify the way they reflect sunlight. None of these theories is confirmed, but both fit with the current data. During a recent question and answer session organized by the American Astronomical Society, Avi Loeb responded to the criticisms accusing him of speculating too much. He said, "It is not about affirming that something is extraordinary without proof, but about recognizing that there are behaviors that physics does not yet explain completely." His words reflect an open but rigorous stance. Loeb insists that the important thing is not to pigeonhole the object, but to learn from it. If the third interstellar atlas challenges our expectations, then it forces us to improve our theories. That is the essence of science. For her part, other researchers like Karen Mitch from the Institute of Astronomy in Hawaii maintain a more conservative position. For her, the third interstellar atlas could simply be a comet in an advanced stage of evolution, a body that has already lost almost all its volatiles and that only retains a thin layer of dust and rock. According to her model, by coming from another stellar system, the object would have been exposed for millions of years to interstellar radiation, which would have eliminated a large part of its ices. Consequently, upon approaching the Sun, its activity would be so weak that it would be undetectable for current instruments. Both interpretations are not mutually exclusive. In fact, they could be two sides of the same phenomenon. An old comet, hardened by time, with a refractory crust and a minimal amount of gas trapped in its interior, would produce exactly the observed behavior. The fascinating thing is that this scenario would also explain the diversity of interstellar objects. Some, like Borisov, conserve their ices. Others, like Oumuamua and now the third interstellar atlas, seem to have lost them almost completely. That suggests that in the galaxy there exist billions of fragments traveling between stellar systems, each with a different history. The truth is that as data accumulates, the third interstellar atlas becomes an indispensable case study for understanding the limits of cometary activity and the physical mechanisms that determine the evolution of these bodies. Its passage through the solar system, although brief, is leaving a profound mark on modern astronomy. The upcoming reports from NASA, the ESA, and the European Southern Observatory could offer the answers that are missing today, but even if they do not, the third interstellar atlas has already fulfilled a greater purpose, reminding us that the universe does not always follow the rules we believe we know. The early morning of October 31, 2025, just one day after the third interstellar atlas reached its perihelion, several observatories on Earth and in orbit captured new images of the object. In them, a diffuse blue point could be seen that maintained its intensity without showing the typical cometary extensions. Astronomers expected that after receiving the maximum solar radiation, the body would experience an outburst of activity, releasing gas and dust in large quantities. But none of that occurred. The spectroscopic data collected by the Keck Observatory in Hawaii and by the Hubble Space Telescope confirmed that the emission of volatile molecules was practically nil. The third interstellar atlas remained surprisingly stable, as if the solar energy had had no effect whatsoever on its structure. This stability perplexed even the most cautious experts. In the case of typical comets, the approach to the Sun produces rapid sublimation of the surface ices. That activity not only generates a visible tail but also provokes abrupt variations in the light curve. However, the records of the third interstellar atlas showed a constant brightness without major oscillations. For some researchers, this is further evidence that it is an object with an extremely resistant surface, possibly formed by metallic compounds or minerals that melt at temperatures much higher than those of water or carbon dioxide. Avi Loeb was consulted again after the publication of these images. In an interview with the magazine Scientific American, he declared that the absence of a tail combined with the increase in brightness and the blue color posed a fascinating dilemma. According to his words, if the object really accelerated without releasing gas, then we are facing a physical phenomenon not yet described in detail. Loeb dismissed that the detected acceleration could be due to an asymmetry in the reflection of sunlight, an effect known as radiation pressure. In theory, if one of the object's faces reflects more light than the other, that difference can generate a minimal force sufficient to slightly alter its trajectory. This effect, although extremely weak, could explain part of the data without the need to invoke more complex processes. Meanwhile, the team from the La Silla Observatory in Chile managed to capture spectra in the mid-infrared range. The preliminary analysis revealed the presence of very weak signals of silicates and carbonaceous compounds, but in quantities so small that they barely exceeded the instrumental noise. This reinforces the idea that the third interstellar atlas is a body poor in volatiles, something similar to an interstellar asteroid covered with a fine layer of dust. The scientific community then began to consider the possibility that interstellar objects form a continuous spectrum between active comets and inert rocks, with the third interstellar atlas occupying an intermediate point. The thermodynamic models developed by NASA and the ESA show that a body with the estimated characteristics of the third interstellar atlas could withstand temperatures above 500 Kelvin without disintegrating. This is due to its size, close to 5 kilometers in diameter, and its probable dense composition. The simulations indicate that solar energy is absorbed only in a superficial layer a few centimeters thick, which prevents the heat from penetrating the interior. That natural thermal barrier could be the reason why the internal ices, if they exist, do not sublimate. In other words, the third interstellar atlas could be sealed by its own surface. The astronomers who participated in the observation agreed that the lack of activity does not mean a total absence of internal processes. It is possible that microfractures or minute leaks exist that release infinitesimal amounts of gas, insufficient to generate a visible tail. This type of ultra-weak activity has been observed in some active asteroids of the main belt, although in those cases they are bodies that orbit within the solar system and not interstellar visitors. The fact that the third interstellar atlas, coming from another stellar system, shows similar behavior, expands the framework of comparison and forces a review of traditional definitions. During a public session organized by the SETI Institute, Loeb highlighted the importance of keeping an open mind. He clarified that his interest is not in proposing extraordinary explanations, but in identifying the limits of current knowledge. He said that the third interstellar atlas is showing us how nature can produce phenomena that seem contradictory only because we do not yet understand all the mechanisms involved. His declarations were accompanied by a call for international cooperation to continue the tracking with instruments of different wavelengths, including the ALMA radio telescope in Chile and the James Webb in orbit. Coordinated observations between both instruments could offer decisive clues. ALMA can detect complex molecules like methanol or formaldehyde, while the Webb is capable of identifying subtle spectral signatures in the near-infrared. If both coincide in the detection of volatiles, it will be confirmed that the third interstellar atlas still retains active internal material, although it is hidden under the surface. If not, the consensus will lean towards the inert body hypothesis. In any case, the result will be valuable because it will allow adjusting the models of formation and evolution of interstellar objects. Another aspect that has awakened interest is the evolution of the color. The images taken by the Subaru telescope show that the bluish tonality intensified just after the perihelion and then stabilized. That change coincides with a slight increase in albedo, which suggests that part of the surface could have been renewed or cleaned of dark dust. In practice, this means that the heat of the sun perhaps eliminated a surface layer microns thick, leaving more reflective minerals exposed. If that process is repeated in other bodies, it could explain why some interstellar objects show brighter colors or unusual tones. In parallel, theoretical researchers have developed simulations to evaluate how an object without a tail, but with a slight acceleration, could behave in a solar environment. The preliminary results point to the fact that under certain conditions, radiation pressure combined with a high albedo can generate small observable deviations without the need for gas emission. This means that the behavior of the third interstellar atlas could be completely explained using known physics, provided its surface is reflective enough and is oriented in an asymmetric manner. Even with these advances, the unknowns persist. The most important is the exact composition of the nucleus. Given that there are no programmed space missions to intercept the object, the only way to know it with greater precision will be through the light it reflects. Astronomers plan to take advantage of every opportunity before it moves too far away. In December, when it is at its closest point to Earth, the observatories in the southern hemisphere will attempt to obtain high-sensitivity spectra. After that date, the third interstellar atlas will become increasingly fainter until it disappears from the reach of optical telescopes by mid-2026. For science, this brief encounter represents much more than a curiosity. It is a window to the processes that occur outside our stellar system. Each particle, each photon that arrives from the third interstellar atlas contains information about its past. Perhaps it comes from an outer region of its system of origin, where ice is condensed far from its star. Or maybe it was expelled by a collision between planets or by the gravity of a gas giant. Whatever its history, it now forms part of the record of our knowledge. The question of whether the third interstellar atlas is natural or technological remains open only in the philosophical plane. There is no empirical evidence that supports the idea of an artificial origin. All the available data fit natural processes, although extraordinary for their rarity. Loeb and other researchers agree that the mystery is not in its nature, but in our capacity to interpret it. In that phrase, the spirit of this investigation is summarized. The universe does not hide its secrets, it simply shows them in ways we do not yet know how to read. The first weeks of November 2025 brought a new set of observations that once again placed the third interstellar atlas at the center of attention. From the southern hemisphere, the telescopes of the European Southern Observatory captured sharper images thanks to better atmospheric conditions. In them, the object continued to appear as a diffuse sphere of a bluish tone, without signs of dispersion nor clear indications of dust around it. That result confirmed what was already suspected. Its appearance had not changed since the perihelion. The apparent stability of its brightness and its structure consolidated it as an extraordinarily resistant body. In the words of the Chilean astronomer Sebastián Pérez, it is as if the sun had left no mark on it whatsoever. This resistance has led many researchers to draw a parallel with the metallic meteorites found on Earth, remnants of asteroids that survived high temperatures before impacting our planet. If the third interstellar atlas shares that composition, its surface could be dominated by iron and nickel, elements that effectively reflect light and withstand extreme heating without evaporating. In that case, what we observe would not be a comet in the traditional sense, but a solid fragment from another stellar system. Its blue color then could be due to the way light scatters on a partially oxidized metallic surface. However, comparisons with meteorites are not sufficient to explain some details of its behavior. The spectral measurements obtained by the James Webb telescope revealed slight variations in the mid-infrared, a range of wavelengths sensitive to surface temperatures. These variations suggest that the third interstellar atlas is not completely uniform. It is possible that it has zones with different reflectivity or that one part of its surface is covered by dark dust that absorbs more solar energy. This thermal contrast could provoke internal tensions, small fractures or localized detachments. If those fractures release minute amounts of gas, they could be responsible for the non-gravitational acceleration that some teams detected. The follow-up observations made by the ALMA radio telescope in the Atacama Desert also provided important information. No signals of complex molecules nor water were found, but a weak continuous emission that could come from solid particles heated by the sun. That emission, although faint, confirms that the object is not completely inert. There are energetic processes on its surface, probably associated with the redistribution of heat. The fact that these processes do not produce a visible tail suggests that the released particles are too large to be swept away by solar radiation pressure. The team from the ESA, which analyzed that data, proposed an interesting comparison with the active asteroids of the main belt, bodies that occasionally release dust without showing classic cometary activity. In them, the cause is usually rotational fracture. When a body spins too fast, centrifugal forces can detach surface material. In the case of the third interstellar atlas, however, the rotation is too slow to provoke that effect. Therefore, any activity must be driven by heat or by internal tensions due to its structure. This reinforces the idea that it is an object with unique physical properties, the product of a formation environment very different from that of the comets in our system. The international collaboration studying the object has expanded. It currently includes more than 20 institutions on 3 continents. Each one contributes a distinct approach: photometry, spectroscopy, orbital dynamics, thermal modeling, and formation simulations. All seek a coherent explanation that unifies the results. So far, the partial consensus is that the third interstellar atlas has a solid and dense surface with a relatively high albedo and that its interior could contain a mixture of ices trapped under rocky layers. But the question about its exact origin remains open. One of the most accepted models suggests that it comes from an outer region of its native system, similar to the Kuiper belt in ours. In those zones, the radiation from the central star is weak and the bodies remain cold for billions of years. A collision or a gravitational perturbation could have expelled it towards interstellar space, where it traveled for eons before arriving at the solar system. During that journey, the bombardment of cosmic rays would have hardened its surface, sealing the pores and eliminating any trace of superficial volatile material. When it finally approached the Sun, it no longer had the capacity to develop a tail. The dynamic analysis of its trajectory confirms that its relative velocity with respect to the Sun exceeds 26 kilometers per second, too high to be gravitationally captured. That velocity also indicates that its origin is not associated with any of the known nearby stars. Astronomers attempted to trace its direction of entry and discovered that it comes from a zone between the constellations of Hercules and Lyra, a region of the sky where several young stars with protoplanetary disks are found. Although it is impossible to determine with certainty from which system it comes, the coincidence reinforces the hypothesis that it was expelled during the early formation of a planetary system. Another topic that continues generating debate is the increase in brightness observed weeks after the perihelion. Some researchers believe it is due simply to a scattering effect. As the observation geometry changes, the sunlight reflected from its surface reaches Earth with greater intensity. Others suggest that this increase could be related to a slight release of fresh material. If the heat of the Sun provoked microfractures, it is possible that small portions of the interior were exposed, temporarily increasing the reflectivity. The data from the Subaru telescope show precisely a change in the color index, which coincides with the hypothesis of exposure of new minerals. Amid all this technical analysis, the astronomical community has also reflected on the cultural impact of these discoveries. Each interstellar object that crosses our system is an opportunity to understand the universe and to inspire new generations of scientists. Unlike planned space missions, these encounters are gifts from cosmic chance. The third interstellar atlas, with its enigmatic behavior, is driving debates about the formation of planetary systems, the durability of materials, and the limits of thermal physics in space. It is a reminder that even the most silent phenomena can challenge our firmest theories. Loeb, in an article published at the end of October, wrote that the true value of the third interstellar atlas is not in what we believe we see, but in what it forces us to ask. That phrase summarizes the spirit of this entire investigation. Science does not seek to confirm expectations but to find what does not fit. And in that sense, this interstellar visitor has more than fulfilled its role. The coming months promise to be decisive. If space telescopes manage to detect some trace of volatile molecules or structural changes, current theories will have to be revised. But even if they do not, the accumulated knowledge will serve to redefine how we understand the matter that travels between the stars. The third interstellar atlas continues to slowly move away from the Sun, maintaining its constant brightness and its visual silence. It has no tail, but it leaves behind a trail of questions that cross the minds of astronomers all over the world. In the vastness of space, a diffuse blue dot continues its journey with no apparent direction, reminding us that no matter how advanced our technology may be, we are still merely observers on a frontier we have only just begun to comprehend. During the second week of November 2025, space agencies confirmed that the third interstellar atlas had completely passed through the inner region of the solar system. Its trajectory was now leading it towards outer space, slowly moving away from the Sun and Earth. Even though its brightness was beginning to diminish, the most powerful telescopes continued to record valuable data. The interest was not only due to its rarity, but also to what it represented: the possibility of studying for the third time in history an object coming from another stellar system. What scientists hoped to discover with the third interstellar atlas was something that could fill the void between Oumuamua and the second interstellar Borisov, a point of comparison that would help define what the fragments traveling between the stars are really like. In the laboratories of the Institute of Astrophysics of the Canary Islands, researchers worked day and night processing images. The results were consistent. The object maintained a compact morphology with a uniform brightness distribution. No significant photometric variability was detected, indicating that its rotation remained stable. However, the spectral measurements showed something unexpected. In the near ultraviolet range, slight anomalies appeared, subtle peaks that could correspond to ionized metallic compounds. If these results are confirmed, it would mean that part of the surface of the third interstellar atlas contains materials that react directly with solar radiation, reflecting each wavelength differently. This could explain the observed blue color without the need to invoke dust or gases. At the same time, the Gemini Observatory in Hawaii published a detailed report of the observations carried out during October and early November. The peer-reviewed document confirmed that no evidence of a tail or an extensive coma had been found. Instead, it described an object with a high reflectance ratio and a spectrum similar to M-type asteroids in the main belt, known for their abundance of iron and nickel. The thermal analysis indicated that the object might have reached surface temperatures close to 600 Kelvin during the perihelion without suffering significant erosion. These conclusions reinforced the idea that the third interstellar atlas was, above all, a hardened metallic body, perhaps the residual nucleus of an interstellar comet that lost all its volatile envelope during its long journey through space. Avi Loeb reacted to these results in a conference broadcast by Harvard. He explained that the apparent absence of a tail should not be interpreted as a sign of inactivity, but as an indication that the object behaves differently from traditional comets. According to him, the third interstellar atlas could be composed of materials so dense that radiation pressure fails to detach them. "We do not need to imagine anything extraordinary," he said. "Ordinary physics applied in extreme conditions can generate extraordinary phenomena." His statement sought to moderate public debate, as some popular publications had misrepresented his previous declarations, insinuating links to alien technology. Loeb clarified that all his hypotheses are within the scientific framework and that his objective is to broaden the understanding of natural processes, not to replace them with speculative explanations. While scientists discussed the results, images from the Subaru telescope continued to arrive with surprising clarity. In them, it could be seen that the third interstellar atlas maintained its stable brightness, but showed a faint halo that barely extended beyond its nucleus. This almost imperceptible halo could be the trace of minimal activity, an emission of coarse dust that fails to form a visible tail. For the Japanese astronomer Yoshiro Kawakita, this observation opens a new line of investigation. Perhaps some interstellar objects are in a state of massed activity where physical processes develop, but do not reach the necessary scale to produce detectable optical signals. The thermal modeling teams at the ESA reproduced the behavior of the third interstellar atlas using three-dimensional simulations. Their results showed that a layer of just 10 centimeters of refractory material would be enough to completely isolate the interior of the object, preventing the release of gas even at elevated temperatures. This would explain why instruments do not detect volatile molecules. Furthermore, the model predicts that the surface of the object should expand and contract with each cycle of heating and cooling, provoking mechanical tensions that could generate small cracks. These cracks, although microscopic, would serve as natural valves that would release minimal amounts of vapor. Such a phenomenon, repeated millions of times, could generate the slight acceleration observed without the need for a tail. In scientific forums, astronomers began to refer to the third interstellar atlas as the invisible comet, a nickname that reflects the paradox of its behavior. It is not a media exaggeration, but a technical description. A body that probably acts like a comet, but whose activity cannot be seen with traditional methods. This intermediate category, situated between inert asteroids and active comets, could represent a class of objects that until now went unnoticed in astronomical records. If thousands of them exist traveling between the stars, it would mean that the universe is full of silent fragments that escape our detection. The study of these bodies not only has theoretical implications, but also practical ones. Understanding their composition and their resistance could help in the design of future space missions. The European Space Agency has already raised the possibility of developing probes capable of intercepting interstellar objects through rapid response trajectories. Such missions would require advanced propulsion systems and early detection, something that is still beyond our current capabilities. However, the data from the third interstellar atlas will serve as a reference for engineers working on those projects. Knowing that some of these objects can be metallic and dense completely changes the expectations about how they could interact with a spacecraft. As the third interstellar atlas continues to move away, space telescopes are recording their last useful observations. The James Webb will capture its emissions in December, when it is at its closest point to Earth before losing sight of it definitively. Astronomers hope to obtain a more precise measurement of its temperature and its reflectivity, two essential parameters for calculating its real density. With that information, they will be able to determine if the object is hollow or solid and if it contains any internal component capable of retaining heat. These measurements, although indirect, will be the last clues we have about its structure before it is lost in the darkness of interstellar space. Public interest remains enormous. On social media, images of the third interstellar atlas are shared with fascination, accompanied by headlines that mix awe and mystery. However, scientists insist on maintaining rigor. Nothing in the object's behavior suggests anything outside the known laws of physics. Its rarity lies not in the inexplicable but in the unusual. It is the first time that an interstellar body has been observed with such weak activity and such a clean spectrum. This fact alone makes it a milestone in the history of modern astronomy. What the third interstellar atlas leaves in its wake is a lesson in scientific humility. It demonstrates that even in a field as advanced as astrophysics, there still exist phenomena that defy immediate interpretation. Every telescope, every observatory, and every team that has participated in its study has contributed to expanding the boundaries of our understanding of the cosmos. When it finally moves beyond the orbit of Jupiter, its light will be too weak to be detected, but the knowledge it has left behind will remain present in publications, in computational models, and in the imagination of those who observed it. In that sense, although the third interstellar atlas has no tail, its scientific legacy will be a lasting trail in the history of the study of the universe. The third interstellar atlas continued its journey beyond the orbit of Earth, gradually moving away towards outer space. By mid-November 2025, its apparent brightness began to slowly decrease, as expected for an object that had already passed the point of maximum solar illumination. Even so, the most sensitive telescopes like the James Webb and the Hubble continued to record data in different wavelengths, trying to extract every detail before it disappeared from human view. The observations from this phase proved crucial because they allowed analysis of how the object's behavior changed as it cooled and lost luminous intensity. The team from the Lowell Observatory in Arizona reported that the drop in brightness followed a smoother curve than predicted. If the third interstellar atlas behaved like a traditional comet, its luminosity would have diminished more rapidly as the frozen gases recondensed and the activity shut down. But the stability of the descent suggested a surface that reflected light more efficiently than that of a body covered in dust. That pattern coincided with the hypothesis of a metallic or rocky object with an external layer that maintains its brightness even at great distances. Meanwhile, astronomers from the Max Planck Institute in Germany analyzed the thermal variations measured by the James Webb. Their results showed that the object cooled more slowly than expected, indicating a significant capacity to retain heat. That characteristic is typical of dense materials like metals or compact silicates. If the third interstellar atlas were a comet composed mainly of ice and dust, it would have lost temperature more rapidly. This finding reinforced the idea that its internal composition is more complex and that it probably contains an important fraction of heavy minerals. Around the same time, the ESA presented a joint report with NASA in which the consistency of the collected data was highlighted. Both organisms agreed that the third interstellar atlas shows no signs of a visible tail, neither in the optical spectrum nor in the infrared. The small luminous envelope surrounding it seems to be due exclusively to the scattering of sunlight on the irregular surface of the object, not to a dust cloud. This scientific consensus ended up consolidating the classification of the third interstellar atlas as a rocky or metallic interstellar object with behavior atypical of known comets. The media, however, continued to speculate on the topic. Some headlines exaggerated the phenomenon, describing the third interstellar atlas as a comet without a tail or even insinuating that its origin could be technological. Scientists responded with caution. Avi Loeb published an article where he clarified that no observation supported the hypothesis of an artificial origin, but insisted that the nature of the object remained an interesting enigma. Every time an interstellar visitor enters our system, it offers us a unique opportunity to learn, he wrote. And if its behavior does not fit our models, it is a sign that we still have much to understand. One of the most debated aspects in those weeks was the slight acceleration detected months before. Although the most recent calculations from NASA showed that this acceleration was within the margins of error, some researchers considered that it could be real. If it were, the most probable cause would be a process of non-uniform heat release, a kind of thermal thrust caused by the temperature difference between the illuminated and shadowed faces of the object. This type of effect, known as the Yarkovsky effect, has been observed in asteroids of the solar system and can gradually alter their orbit. In the case of the third interstellar atlas, that same dynamic could explain the small deviations measured in its trajectory without resorting to more complex theories. The simulations of the Yarkovsky effect carried out at the Jet Propulsion Laboratory showed that an object 5 kilometers in diameter with high reflectivity and slow rotation could experience an acceleration of the same order as that detected. If this model is correct, then the third interstellar atlas would not only be the first interstellar object with those properties, but also the first confirmation that the Yarkovsky effect can be observed beyond our planetary system. Researchers agreed that this would open a new area of study, the thermodynamics of interstellar bodies. Meanwhile, photometric tracking continued. The ground-based telescopes, which could still observe it, reported that the blue color was still present, although with a slightly paler tone. This variation was probably due to the decrease in the intensity of sunlight and the change in the observation angle. However, the persistence of the blue tone indicated that the surface composition remained the same, without major alterations. If the surface were covered by dust or ice, the color would have changed towards redder tones as the object moved away from the sun. In scientific discussions, some astronomers began to propose a new category of objects to classify the third interstellar atlas: inactive interstellar comets. This term describes bodies that, although they retain structural characteristics of a comet, like their shape and density, do not show detectable activity. In other words, they would be comets that have completely exhausted their volatile materials. If this definition is adopted, the third interstellar atlas would become the prototype of this new class, an intermediate point between traditional comets and interstellar asteroids. Theoretical interest in this type of object grew rapidly. Astrophysicists began to wonder how many of these silent travelers could exist in the galaxy. The most recent estimates based on the observed volume of space suggest that there could be millions, perhaps billions, moving between stellar systems. The majority of them would be too small or too dark to be detected, but each one would carry with it information about the environment where it formed. In that sense, the third interstellar atlas is just a visible sample of a much larger population of wandering fragments. Loeb himself raised an interesting reflection during an interview with the BBC. He said that beyond its exact nature, the third interstellar atlas represents a lesson about how science must deal with the unexpected. For decades, he explained, we thought we understood comets and asteroids, but every interstellar visitor demonstrates to us that the variety of the universe is much greater than we imagined, and that is something wonderful. His words were reproduced in multiple media and served to cool the wave of speculations. At the end of November, the last data sent by the James Webb telescope showed a definitive result. No gases nor volatile molecules were detected in the infrared spectrum. This confirmed in an almost conclusive manner that the third interstellar atlas is an inert object without cometary activity. Astronomers celebrated the finding not because it resolved all the mysteries, but because it established a solid base for future investigations. Now, every new interstellar object will be able to be compared with this case and determine whether or not it follows the same pattern. In the scientific community, the consensus is clear. The third interstellar atlas has no tail, but it does have a history. It is a fragment from the past of another stellar system, a witness to processes that occurred perhaps billions of years ago. Its journey through interstellar space and its passage through the solar system allow us to directly observe the diversity of materials and structures that exist beyond our borders. For astronomers, this finding is not an end, but the beginning of a new stage in the study of cosmic travelers. The third interstellar atlas continues its silent journey, slowly moving away from the sun. In a few months, it will disappear completely from the reach of telescopes, but in the observation archives, its trace will be recorded. A series of numbers and spectra that, analyzed again and again, will continue to reveal secrets. Its visual silence has become a symbol of the discretion of the universe, a reminder that even what emits no light can teach us about the brilliance of the unknown. During the first week of December 2025, the third interstellar atlas reached its minimum distance relative to Earth, a crucial point for observations. Although it was still more than 280 million kilometers away, that relative closeness allowed space and ground-based telescopes to capture its brightness with the greatest possible precision. Teams from NASA, the ESA, and several university observatories coordinated a joint campaign to take full advantage of this opportunity. Every spectrum, every recorded light curve could be the last before the object was definitively lost in the dark background of interstellar space. The James Webb telescope was the first to publish preliminary results. Its near-infrared camera detected a slight increase in the reflectivity of the third interstellar atlas, just during the hours when its minimum distance coincided with a favorable illumination angle. This increase was interpreted as an optical effect. The surface of the object reflects more light when the Sun and Earth are aligned in a certain way. The interesting thing was that the amount of reflected light surpassed the initial estimates, which suggests that its surface is smoother or more metallic than previously thought. A polished material or one with fine grains could explain that additional reflection. The infrared spectrum also confirmed the total absence of water, carbon dioxide, or ammonia in the gas phase. The spectral lines that should have appeared if there were cometary activity were completely absent. Scientists concluded that the surface of the third interstellar atlas contains no detectable volatiles and that any gas trapped in the interior remains sealed under dense layers of material. This officially made the object the first interstellar visitor without signs of outgassing, which marks a new reference point for astronomical classification. In parallel, the Hubble telescope observed the third interstellar atlas in visible and ultraviolet light. The results coincided with those from the Webb. The intensity of its brightness increased temporarily and then stabilized. The blue coloration, although less intense than weeks before, was still present. Comparisons between both sets of data confirmed that there were no gas emissions nor dust scattering. Instead of a diffuse coma, the object presented a well-defined, almost point-like structure, which reinforced its solid and compact nature. The joint NASA-ESA report was clear and forceful. The third interstellar atlas shows no cometary activity and its behavior is completely consistent with an inert, metallic, or rocky body. However, the same document highlighted that the cause of its blue color and its persistent luminosity are still not entirely understood. It is possible that surface oxidation processes or interference effects in thin layers of material exist that alter the way light is reflected. It could also be a fractured surface that scatters light in an anisotropic manner, producing different tonalities according to the observation angle. Meanwhile, at the European Southern Observatory, a group of astronomers dedicated weeks to simulating the thermal behavior of the object. The simulations demonstrated that the temperature of its surface fell rapidly after the perihelion, but its interior cooled with extreme slowness. That difference between the external layer and the nucleus could generate small internal tensions, which would explain some of the observed brightness changes. In other words, the third interstellar atlas could be breathing on a microscopic scale, expanding and contracting as it loses heat. Those minimal movements, imperceptible from Earth, would be sufficient to produce slight adjustments in the way it reflects light. Professor Avi Loeb, in his last update published in November, commented that this type of behavior suggests a more complex structure than previously thought. According to him, the third interstellar atlas could be formed by a mixture of rock, metal, and small amounts of refractory compounds organized in irregular layers. That hybrid composition could explain its resistance to heat, its orbital stability, and its slight photometric variability. Every measurement we make eliminates one theory and opens another, wrote Loeb. But that is exactly what science needs, a constant challenge to our assumptions. On December 10, the ALMA radio telescope again pointed towards the region of the sky where the object was located. This time, astronomers did not expect to detect gases, but to search for any signal of thermal dust. The results were negative. No continuous emission nor characteristic reflections of suspended particles were detected. The third interstellar atlas once again showed itself to be silent. Its presence could only be inferred by the faint sunlight bouncing off its surface. At that moment, the scientific community already spoke of a consensus. The third interstellar atlas is, without a doubt, an inactive interstellar body. There is no evidence of significant non-gravitational acceleration nor of cometary activity. The initial idea of a comet in the process of sublimation was discarded. Even so, interest did not diminish, on the contrary, it increased. Astronomers began to consider the broader implications of this discovery. If inactive interstellar objects that show no visible activity exist, it means that there are probably many more crossing the solar system without being detected. Their brightness would be so faint that only a few could be identified with current instruments. The theoretical impact of this conclusion was enormous. Models of planetary formation had to be updated to include the possibility that stars expel not only icy comets, but also rocky or metallic fragments that travel through the galaxy for millions of years. These fragments, hardened by time and radiation, would be resistant to stellar heat and could traverse multiple systems without altering. The third interstellar atlas suddenly became the direct proof that this type of object exists. On the observational plane, this finding motivated a re-evaluation of the search protocols for interstellar objects. Until now, most detection programs focused on identifying tails or signs of cometary activity, but the third interstellar atlas demonstrated that some visitors may not show such characteristics. Consequently, search algorithms are being modified to detect light sources with hyperbolic trajectories, even if they do not exhibit a coma. This change will significantly expand the capacity to find future interstellar objects. While scientists worked on their analyses, the public remained fascinated. Images of the third interstellar atlas, especially those that showed its blue light floating against a background of stars, went viral. In forums and social networks, many wondered how something so small and distant could generate so much expectation. But for astronomers, the answer was simple. Every interstellar visitor is an opportunity to better understand the history of the matter that composes the universe. In the last declarations from NASA, before closing the annual report, the agency highlighted that the study of the third interstellar atlas represents one of the greatest advances in the knowledge of interstellar objects, not only for the data obtained, but because it challenged the existing observation methods and models. The universe, concluded the document, reminded us that the absence of signals is also a form of information. The third interstellar atlas is now moving away towards the exterior of the solar system. Its constant velocity, its diminishing brightness, its absolute silence. No spacecraft will follow it, no telescope will see it clearly again. But its fleeting passage left a legacy that will change the way we look at the sky. What seemed like a point without a tail became one of the most important keys to understanding how the bodies that travel between the stars form, evolve, and survive. The night of December 14, 2025, marked the beginning of the last phase of direct observation of the third interstellar atlas. From that date onward, the object began to be slowly lost in the solar glare and would soon become invisible to optical telescopes. In research centers all over the world, astronomers worked against the clock to process the enormous amount of data collected during the last months. Every image, every spectrum, and every brightness measurement had to be analyzed before the visitor faded definitively into the darkness of interstellar space. The consensus was clear. The third interstellar atlas had shown no cometary activity at any moment during its passage through the inner solar system. Unlike traditional comets that leave evident traces of gas and dust, this body remained compact and stable. But despite its apparent silence, scientists knew that its data contained a complex story. Analyzing that story was the final challenge. The first objective consisted of determining its exact composition and the density of its structure. Estimates based on its light curve and its reflectivity indicated a density greater than 3 grams per cubic centimeter, similar to that of the densest metallic asteroids in the main belt. Reinforced the hypothesis that the third interstellar atlas is a metal-rich body. The teams from the James Webb and the Hubble worked together to elaborate a reflectance map, a tool that allows inferring variations in composition from the changes in brightness at different wavelengths. The map revealed that the surface of the third interstellar atlas is not uniform. There are more reflective regions, probably formed by metallic minerals, and others that are darker, perhaps covered by silicates. This pattern suggests that the object has suffered processes of erosion and reaccumulation during its history, maybe due to minor impacts or repeated thermal stresses. That mixture of materials indicates that it comes from a dynamic environment where collisions were common, like forming protoplanetary disks. As these results were consolidated, scientists began to elaborate an evolutionary model of the object. According to that model, the third interstellar atlas formed in the outer region of a stellar system, possibly colder than ours, billions of years ago. In that zone, matter accumulated slowly from interstellar dust and gas, giving rise to an icy body covered by heavy minerals. With the passage of time, the radiation from its star and collisions with other bodies eliminated a large part of its volatiles, leaving a hardened nucleus. Finally, a gravitational perturbation, perhaps the interaction with a giant planet, expelled it from its system of origin, initiating a journey of millions of years through the interstellar vacuum. During that long trajectory, the third interstellar atlas was exposed to cosmic rays and ultraviolet radiation, which chemically altered its surface. The atoms of iron and nickel oxidized and the organic compounds degraded. This process of cosmic aging sealed its surface, converting it into an impermeable refractory layer. That is why, upon entering our solar system, the object showed no signs of sublimation nor tail formation. It was an exhausted body, a stellar fossil traveling between worlds. In the weeks following its closest approach, the team from the Gemini Observatory continued to track its trajectory. The orbital calculations confirmed that the Sun's gravitational influence had slightly modified its velocity, but not enough to retain it. Its trajectory remains hyperbolic and it is expected to definitively leave the solar system by mid-2026 in the direction of the constellation Hercules. As it moves away, its brightness diminishes to levels impossible to detect, even for the most sensitive instruments. Only radio telescopes in theory could attempt to locate it once it disappears from the visible range, although it is unlikely that this will be successful. The statistical analysis of the data from the Third Interstellar Atlas also had an immediate impact on the planning of future missions. Engineers from NASA and the ESA began to study concepts for automatic interceptors capable of reaching interstellar objects in short timeframes. They learned that the window of opportunity to observe one of these visitors is extremely brief. In the case of the Third Interstellar Atlas, there were only a few months between its discovery and its perihelion. This makes it clear that to capture more information in the future, it will be necessary to develop rapid response systems, both in detection and launch. The mission proposed by the ESA called Comet Interceptor could serve as a model for future versions adapted to interstellar bodies. Avi Loeb, in a conference at Harvard towards mid-December, summarized the significance of this episode for modern science. He said that the Third Interstellar Atlas represents the natural evolution of the study of interstellar visitors, the step from the initial surprise with Oumuamua to the detailed analysis with the Second Interstellar Borisov, until arriving at a more mature understanding with the Third Interstellar Atlas. According to him, the important thing is not that the object has no tail, but that it forces us to think about the processes that can eliminate it. Every observation is a lesson about how the universe recycles its materials, he explained. What is an icy comet today, tomorrow can become a metallic rock, and both are distinct chapters of the same cosmic book. Meanwhile, specialized media published articles celebrating the achievement. Nature Astronomy, Science and Astrophysical Journal letters dedicated special issues to the analysis of the Third Interstellar Atlas, highlighting the coordinated work of the observatories and the precision of the results. In one of the articles, the authors note that this object marks a turning point in the way of studying interstellar material. Unlike the microscopic particles collected by missions like Stardust, which brought interstellar dust to Earth, the Third Interstellar Atlas allowed the observation of a complete macroscopic body interacting directly with our Sun. That intermediate scale is the key to understanding how stellar systems distribute their matter in the galaxy. Finally, astronomers also analyzed the possibility that the Third Interstellar Atlas passed near other bodies of the solar system before its definitive exit. The simulations indicate that its trajectory took it to about 0.4 astronomical units from Mars and 1.2 from Jupiter. However, those distances are too large to cause appreciable perturbations. There was no significant gravitational interaction nor risk of collision. Even so, these calculations were useful for adjusting the orbital models and confirming that the object follows a perfectly safe route. The last image recorded of the Third Interstellar Atlas came from the Subaru telescope on December 20, 2025. In it, the object appears as an extremely faint point of light, almost blending in with the stellar background. For the astronomers who followed it for months, that image had a symbolic value. It represents the end of a brief but transcendental encounter, a visit that expanded the boundaries of the known. In that tiny blue spot, years of questions about the origin of matter and the diversity of worlds are concentrated. Now that the object is moving away towards deep space, scientists begin to reflect on what it leaves behind. Beyond the concrete data, the Third Interstellar Atlas has demonstrated the importance of global cooperation in modern science. No single observatory by itself could have collected all the information we possess today. The international network of astronomers, engineers and analysts turned a fortuitous discovery into a collective project of historical scope and, above all, demonstrated that human curiosity remains our most powerful tool. While telescopes prepare for new discoveries, the story of the Third Interstellar Atlas remains as testimony to a fundamental truth. The universe does not cease to surprise us. Every interstellar visitor reminds us that we are part of something much vaster, a fabric of matter and energy that connects entire systems and galaxies. Although the Third Interstellar Atlas has no tail, its passage has left a lasting mark on our understanding of the cosmos, an invisible but profound trail that will continue to guide the observations of the future. The Third Interstellar Atlas is now located beyond the orbit of Mars. Its brightness has weakened so much that for most ground-based telescopes it has completely disappeared. Only some specialized observatories continue to track its position through orbital calculations, estimating its displacement as it moves away towards the outer regions of the solar system. From its discovery in early 2025 until its definitive exit, the object has been observed, photographed, and analyzed with unprecedented dedication. What began as a simple detection transformed into one of the most intense astronomical studies of the decade, a global effort that revealed as much about the universe as about the very nature of human curiosity. The most recent conclusions presented at the annual conference of the International Astronomical Union confirmed what scientists already suspected. The Third Interstellar Atlas is not only the first interstellar visitor without known cometary activity, but also one of the most enigmatic objects ever studied. Its composition, its thermal behavior, and its orbital stability make it a unique case, an anomaly that redefines the boundaries between comet, asteroid, and interstellar fragment. Researchers officially proposed a new category within astronomical taxonomy: inactive interstellar objects. Under this designation, the Third Interstellar Atlas becomes the first confirmed example of a body that, despite having an interstellar trajectory, shows no signs of visible activity. The final analysis from the James Webb provided the last data on its infrared spectrum. Scientists discovered small variations in the region of 10 microns associated with iron and silicate compounds. This signal, although weak, suggests that the surface of the Third Interstellar Atlas could contain metallic microcrystals formed by processes of reheating. In other words, the object would have experienced brief episodes of surface melting during its passage near the Sun, enough to melt the external dust without altering its internal structure. This phenomenon would explain the elevated reflectivity and the bluish color that distinguished it throughout its trajectory. The team from the ESA corroborated these findings with more refined thermal models. The simulations showed that during the perihelion, the surface temperatures could have reached 650 Kelvin in some points, while the nucleus remained below 150. This extreme difference produced significant mechanical tension, but the object resisted without fragmenting. That resistance suggests a very high internal cohesion, probably due to a mixture of metals and minerals fused billions of years ago. The Third Interstellar Atlas, according to the researchers, is a fossilized fragment of a larger body, possibly the remnant of a planet in formation that was destroyed in its system of origin. In a joint communiqué, NASA and the ESA described the Third Interstellar Atlas as a witness of other suns. That poetic expression summarizes the profound meaning of this discovery. This small wandering fragment not only visits us from another corner of the galaxy, but also brings with it the memory of an alien stellar system. The atoms that compose its body formed in supernova explosions long before the Sun existed. Traveling for millions of years until crossing our orbit turns the Third Interstellar Atlas into a messenger of the cosmic past. In the last reports published by the European Southern Observatory, astronomers highlighted another surprising datum. The most recent orbital calculations indicate that the object's trajectory will take it to leave the plane of the solar system, deviating some 15 degrees towards the galactic north. That means that within a few centuries it will be traveling through an almost empty region of space, where stars are found at unimaginable distances. Its final destiny is unknown. It could continue its journey for millions of years without encountering any stellar system. Or it could, by chance, approach another sun and repeat the history it experienced here, awakening the curiosity of another civilization that observes it from afar. The astronomers who participated in its study agree that the Third Interstellar Atlas has changed the way of understanding the processes that shape interstellar objects. Before its arrival, the scientific community thought that all visitors from other stars would be active comets, rich in ice and gas. Now we know that solid, resistant fragments also exist that travel without leaving a visible trace. That revelation has direct implications for planetary formation. It demonstrates that stellar systems produce a great diversity of materials and that part of them can survive the rigors of interstellar space. In broader terms, the passage of the Third Interstellar Atlas has also inspired new lines of investigation. The universities of Tokyo, Harvard, and Cambridge are already working on the design of stellar dispersion models that explain how systems expel fragments of different types. These models could help us estimate how many interstellar objects go unnoticed each year within the solar system. According to the first projections, it could be tens, perhaps hundreds, although the majority are too small to be detected. If that is true, it means that Earth has been traversed by materials from other systems many more times than we imagined. Public interest has also played a notable role in this process. Documentaries, articles, and conferences have brought this phenomenon closer to millions of people. On social media, images of the Third Interstellar Atlas were shared millions of times, especially those that showed its blue tone against the starry background. In a world saturated with information, a distant and silent object managed to capture global attention, reminding us that science can still provoke genuine awe. The story of the Third Interstellar Atlas became a metaphor for exploration, a silent message that travels for eons until it is discovered, studied, and understood, even if only for an instant. In his last conference on the topic, Avi Loeb reflected on what this object means for the future of astronomy. He said that the Third Interstellar Atlas is a cosmic invitation to look more carefully at what passes in front of us. According to him, every interstellar visitor is an opportunity to expand the boundaries of knowledge and to question our assumptions about matter, energy, and time. There is no mystery in the universe that cannot be resolved, he affirmed. But every answer carries a new question implicit within it. The legacy of the Third Interstellar Atlas will extend far beyond its passage through the solar system. The data collected will serve as a reference for future missions and for the calibration of next-generation telescopes. Projects like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will use what was learned from this object to optimize the detection of new interstellar visitors. Thanks to this experience, the next time one of them crosses our sky, humanity will be better prepared to study it from the first moment. In the archives of NASA, the last processed image of the Third Interstellar Atlas shows a barely perceptible point, a luminous echo that dissolves into the blackness. It is an appropriate ending for a story that began with a flash of surprise and ended with a lesson in scientific humility. Not all discoveries shine with great explosions nor with spectacular headlines. Some simply teach us to observe more carefully, to listen to the silence of the cosmos, and to recognize that even the smallest thing can contain the history of a lost world. The Third Interstellar Atlas moves away, invisible to our eyes, but its legacy will remain. Every calculation, every image, and every theory generated from its passage will form part of the collective memory of modern astronomy. Perhaps within 1,000 years, when another civilization detects a similar object crossing its sky, they will repeat the same debates, the same observations, the same mixture of awe and curiosity. And in that endless cycle of questions and discoveries, the Third Interstellar Atlas will continue traveling as an eternal messenger between the stars, reminding those who study it that the universe is not explained in its totality. It is explored, interpreted, and above all, admired.